All right, so I saw it now, it's on live on YouTube. So welcome everybody. So hopefully from good afternoon, good evenings, and good mornings to everybody. So it's great to see the overwhelming participant for today's talk. So I don't know how much I need to introduce of today's speaker of our East NLA seminar. So I just talk about my personally. So when I was finishing even at the undergraduate school education around the earlier 1980s, I think one of the very earliest paper I read is from Professor Yousef Saad. And he studied at that time, so was on this, today we all know so-called subspace projection method. He pioneered the fundamental series and the fundamental algorithms. Of course, up to now, I think nobody, particularly in this audience, can say, I don't know what is GMRS is or something like that. So I really don't think we need any further introduction. So it's really a great pleasure. So Professor Yousef Saad from the University of Minnesota. So Yousef, you can take over.
Okay, thank you, Sergeant. Thank you for the very nice introduction. A big thanks to the organizers for inviting me and also for putting all the work to animate this forum. Welcome, everybody. It's good to see everyone. So what I'll be talking about, as you can see from this title, there are 3 different topics, but they all relate to one single problem, which is the large eigenvalue problem, large Hermitian or symmetric real eigenvalue problem. And we'll be talking about the block-Jacobi method, an old topic. And I will be talking about subspace iteration, as well as polynomial filtering a little bit towards the end if I have time. And the common ingredient in all of these is the topic of invariant subspaces. So that what relates all of these. And now I will just start with the Jacobi method. So this is an old method. Jacobi introduced it in 1946. If you look at the where this appeared, it's actually amazing how many items this individual was working on. It was really incredibly prolific. And this is on one of several different things that he was doing at the time. So the method is very simple. You use rotation matrices like these. And if you call B the new matrix that is obtained by after you do the rotation, then you select P and Q to be the largest, or you have the largest entry in A, and you find the rotation that ensures that BPQ is 0, and you apply it. And you repeat the process until you get converged, and then you get convergence. And here, because the norm of the matrix is preserved, the things outside, entries outside the diagonal will decrease, and you can show convergence because of this. So this is just a quick background on this method. So these are a couple of details. Now, in the 1980s, people had a lot of interest in parallel versions. And then also, there was a block version that appeared in the mid-80s. And this is actually very simple to describe. This matrix here, the 2x2 matrix now becomes this. It's like you can extract these blocks that you're interested in. This is a 2x2 matrix, which is extracted from the original matrix. Okay, this one here. This now has become a block matrix, 2x2 block matrix. And then this becomes this. And the only thing you do is you diagonalize this matrix to get zeros in here, and you apply the transformation. It's very simple. It's actually simpler to describe than this, right? And the number of theoretical results have been shown. It's really, a lot of things have been done with Jacobi until so the Jacobi method was dominant until the discovery of the QR in the 60s. That was the only way, that was the main means of computing eigenvalues of a symmetric matrix. And then there was a little revival in the 90s, the parallel computing, and then, but still, it's still not that much discussed today. You know, it basically, it looks like everything regarding the Jacobi has been essentially written, right? The method tends to be a little slower than QR, not a little slower. It's actually substantially more operations. It's maybe a few times more expensive than QR. But it has some advantages. For example, it could be very useful when A is almost diagonal. That's one thing that has been noted by people. And also the other thing, which is well known, is that it is more accurate actually for small eigenvalues. This is work that was done, started by Wilkinson actually, and then Demel and Veselak showed some results in the 90s that show that this is more accurate. But I think what is the more interesting aspect for me is that I believe it has a great potential for GPUs, and I think this is probably overlooked. So this is one of the reasons actually I got to look at this, is trying to see if there is a way of reviving this technique with the view of looking at GPUs. So let's start with looking at the kind of things I'm interested in. So this is the original matrix, and these are the blocks that I called A11, A12, etc. I just changed notation to simplify things a little bit. These are the 4 blocks of interest. And we were going to apply rotation matrices of this form. They're not really, this is no longer a unitary matrix. So you have identities in this location, minus Y here and Y transpose in here, and then this is identity. So this would be very similar to the rotation without there's a name associated with these, I forgot what it's called, but you have, essentially you replace C by 1 in the rotation matrices. So it's an n-scaled kind of rotation matrices. So this is all to say that you're selecting a block that's in this side that doesn't hit the diagonal. It's entirely up in the upper part. And this could be an arbitrary size. You could even take the whole thing if you want, the whole 2 by n over 2 by n over 2 if you like. May not necessarily be worth it, but it's doable. Okay, so that's the notation I'm using. And now if I call this matrix C, this is now a small matrix. I'm going to call this matrix U. And I noticed that U transpose U has this form here. Actually, U is normal. And you have U transpose U has this block in here, which have the form I plus Y transpose, I plus Y transpose Y. So you need to, this is not unitary, therefore you need to post scale and both to the right and to the left. And for this, we just use the Cholesky factorizations of these matrices. Okay, these are positive definite matrices, no problem. And that what I would do, okay? So these are to be added as in addition to applying these. So if you look at the matrix U transpose CU, this is the equivalent of what I showed earlier. If you remember this part in here, this is looking at the 2 by 2 blocks. So if you look at what happens to that, you get this matrix in here. And so I need this to be 0. So I need to solve this equation. This is a Riccati equation. So you might say, why do we have to do something that's so expensive? We could just solve this, use the block version, but there are some advantages in doing it this way. So this is, I need to solve this. And this is an interesting form of the Riccati equation. You may notice that H and M are both symmetric, but they're not of the same size. So the Y matrix here is rectangular. And this matrix here and this one are the same. And they are transpose of each other. So this is a special form. So how do we compare this with the classical block-Jacobi? Remember that in the classical block-Jacobi, all I needed is to transform this matrix to diagonal form. So I'm just diagonalizing this matrix, which I call C. Okay. And in the new approach, we have a special form of truth. So this could be taken advantage of and with slight advantage in cost. I will talk about that later. Also, towards the end, the y, so the g tends to be small, and therefore the y tends to be small. And this could be also exploited. And there's one particular application where this could be quite useful, is in the case where C is close to diagonal. For example, you have a matrix that's almost diagonal, then it's very inexpensive to solve the Riccati equation in that case, or approximately solve it. So any questions about the setting so far? And then we'll go to the theory. And all right, so let's move on with this. So I'll just now talk a little bit about some of the theoretical aspects of this. So as we know, this, by the way, there's a very early work by Analab that showed that you could solve a Riccati equation by solving an eigenvalue problem. And then there were many, many more works after this. This is a well-known topic. The context we're in is slightly different because the Riccati equation is a little bit away from the same, a little bit different than one set up by Analab. So if you go back to here, if I call this matrix, if I factorize this y here, then I call this matrix S. Then I can write the equation this way. So now this is just a standard Sylvester equation, right? But so I'm going to write it this way. But this S here also satisfies an equation. So you could put things together in block form like this. Okay, so that's what I'm looking at. This is a formulation of the problem in the form of an invariant subspace kind of form, right? It's an eigenvalue problem. So I'm trying to find a basis of this form for a certain invariant subspace, and S is just an auxiliary matrix that here. So notation, I'm going to call Z this matrix. I'm going to call E this matrix in here, 0, I, so the same shape, but replacing Y by 0. And P is a projector. I don't think it will be coming up too much in the talk, but it's useful in some other contexts. Okay, so these are the things I need to know. Z is of this form. So then you can show the following result. So Z is the basis of an invariant subspace for C, but you could show the opposite also is true. And so I'm going to use the shorthand here. So essentially, all I need is an invariant subspace of this form. Okay, so when the Riccati equation is satisfied, then this there is an invariant subspace of this form to C. Okay, the opposite is also true. So there exists an invariant subspace of C such that the second part here is you can write this as y1, y2 if you like. Okay, and this has to be non-singular, and then you multiply by the inverse to get identity here. That's exactly what this says here. And then the next thing is, from this theorem I could show the following: the Riccati equation has a solution, no matter what. That equation that I showed earlier always has a solution. And that comes from a very simple fact. It comes from this lemma, and the fact that I can diagonalize this matrix if I use a certain matrix Q, and all I need is I'm going to find this basis of invariant subspace so that this part here is non-singular. That's all I need. Mm-hmm. Okay, I'm writing it together in the same block, but all I need to get something that's non-singular here. Then I will invert that. So it only says that there is such a block that it can be selected among the matrix Q. That's all. It's a fairly simple thing to think about it, but the consequences rather interesting. Any questions?
Yeah,
yeah,
I'm monitoring the chat. So if any of you have a question, feel free to type in the chat. Otherwise, in the end, you can unmute yourself to ask a question.
Okay, so I'll continue with this then. Yeah. All right, so if there are any questions, then I'll continue. So let's look at the methods for solving that Jacobi equation. The first one is obviously the Newton approach, the classical, the standard thing that has been used. These are the equations you get. You need to solve a Sylvester equation at every step. The convergence is obviously quadratic. The thing is that you need to solve a Sylvester equation, which is order n cubed. So, and I observed, this is just observation, that this converges almost, I mean, I think for small matrices, I had never had a problem with convergence. It always converges some erratically. So it indicates that it's probably going to be difficult to show a convergence proof. But then I discovered that for larger matrices, it's not necessarily true. So, but the point is, there's still potential to get this thing to work, this approach to work well, if you know a way of getting a close starting point. Okay, that's the key to getting Newton to work well. Okay, so I'm not recommending this necessarily, except in some scenarios. I'm going to talk about that later. I should also mention that I had working on this had made me rediscover something that I was dimly aware of. And there's a paper by François Chatelain, who was my advisor in the 80s, in 1984, where she talked about computing invariant subspaces. And that's exactly this approach, essentially. It's mathematically equivalent to this. So this is mentioned in the work on Grassmannian manifolds and stuff like that, when the people talk about eigenvalue problems with using the Grassmannian perspective, which I will discuss later. So the second approach that I use is the invariant subspace approach. So I need to get an invariant subspace with a basis of this type, this MATLAB notation, right? So I need to get start with something like this first, and then multiply by the inverse of that matrix. And then I get the identity in here, and then I get minus y in here. So that's the approach. However, I need to get something for which this y2 is well conditioned, because I'm going to invert it. So for this, I would like to use a maximum volume approach. So this is one known technique that people use, where you try to maximize the determinant. So I have a matrix, say a matrix that's like this, all right, squared, and I want to get, this is the goal I'm trying to set up. I'm going to select some columns in here. Let's say they're together, so, okay, such that this is well conditioned. So I have to look at these columns here and select those that are the best conditioned. And there is a very simple approach that's be used in this context, and that's this using the greedy approach, which is essentially a forward-looking version of the Gram-Schmidt method. If you recall, what you do is the standard Gram-Schmidt is backward-looking. You orthogonalize one vector against all the previous ones. And here, what you do for example, in the first step, is I orthogonalize these vectors against this one. Okay, and this one is norm 1. Orthogonalize all these vectors against this one, and I pick the one that has the largest norm, and I repeat. That's all. Really, a very simple process. And so the algorithm is therefore like this: diagonalize the matrix C. Then I'm looking at this matrix Q. I'm looking at the bottom part that, as I was mentioning in here, the bottom part of this Q, and then use this greedy column selection method to select the n2 columns that are the best ones to select, and I get the y from this. I get the z from this y here. Right. That's all there is to it. And this, by the way, is just simply this expression here. Okay. So the computational cost, by the way, I want to mention here something for those of you who are interested in GPUs. This is essentially, most of the work is of this type. Okay, the most important part of the work is to update columns of this in this form, and the Y is the matrix I just talked about. So the Y here is a small, let's say, new by new matrix. It can be square, but doesn't have to be square. And so this could be extremely fast if you do this on GPUs. Okay, and you have also similar things on the right on the rows. Okay, so that's the cost of the algorithm of one step. This is the whole sweep of m by m minus 1 divided by 2, eliminating all the blocks in the upper triangular part. Nu here reflects the cost of the ordering cubed method, or the, for example, the Cholesky factors you have to extract, and also getting the matrix Y. So I put all of those in the form beta nu cube. Beta is some number, I don't care what it is. And the total cost is of this type. This is to compare with this cost in the standard block version. So you gain a little bit of, it's a 25% gain. And the accumulation of the rotations also require the same amount of work. So it's essentially 3n cubed per whole sweep. And you can expect to have maybe upward of 10 iterations in total. Maybe less, maybe more, but it's around, usually a rule of thumb is around 10 outer iterations, all sweeps. That's the cost. So this is now one of the interesting applications of this approach. And let's suppose that I have diagonalized the matrix and I perturb it. So now the matrix has been diagonalized, but now I perturb the matrix by a certain matrix E, which is small in norm, but also it's sparse. So I have, I can compute now the perturbation in this form. So the diagonal, the A tilde is essentially Q times the diagonal plus some perturbation here times Q transpose, and F is this. So this is something you have to compute. E is sparse, you can compute that somewhat inexpensively. And then the application of this could be, for example, if you want to track the eigenvalues of a matrix that's being modified just a little bit. So the goal now is to compute the eigenvalues of this matrix. Okay, so I'm going to put this matrix in this form. This is similar to what we had before, but now this is n by n, okay? And n is the size of the original matrix, so this is a large matrix. All I want is to eliminate this G. And here I'm assuming that I'm going to track new eigenvalues only, so the largest new eigenvalues, and I'm permuting the matrix so that they're in this part in here. So the largest eigenvalues are in here. And the question now is, how do I eliminate this G? And then you could use that approach. Here's one instance where the Newton approach is interesting, because this matrix is almost diagonal. So it's very inexpensive to solve the Sylvester equations in this case, or an approximation by essentially replacing these by diagonal matrices. So the cost is ordered and squared in this case. So you can very easily correct the eigenvalue problem. Here is a very simple example obtained by using this covariance, Mattern covariance matrices. So this is a 32 by 32 grid where you get a matrix of size 1024. And I perturb it with this MATLAB notation here. So roughly five non-zero elements per row. And then I normalize this so that you have roughly 10 minus 2. And here's what you get if you look at the eigenvalue. So this is the mean error, the mean eigenvalue error, the sum of the relative errors. And if you don't do anything, if you just look at the eigenvalues of lambda as the eigenvalues of A tilde, then as you can expect, the errors are like 10 minus 2, 10 minus 3 because of the perturbation. Then if you apply only one step of the method I just described, so this order n squared calculation, you get this improvement, and then 2, 3 steps, you're basically done, getting the full accuracy. So it's very inexpensive to do the correction. Okay, so now a couple more tests with this to finish up with this topic. So this is only an experiment that shows that the number of iterations goes down if the block size increases, the same matrix, and I'm using different block sizes. So it's advantageous to use block sizes that are large at the beginning. And then there's something I want to observe here just to make a point about the conversions. Typically, at the beginning, you have something that's almost linear. It's essentially something you'd expect from looking at the theory. And then all of a sudden, when you have things that are small, then you have onset of quadratic convergence that starts in here. So that's very common. So a lot of the time is taken by the first part. So now this is an important slide. It shows a comparison of all the different methods that I've tried with matrices of different sizes. So this is Newton plus Riccati. The implementation here is a little crude. I just do a certain number of Newton iterations. So it's not too unexpected to have something that doesn't work that well, but it works fairly well for smaller cases in this case. This one is the one that I recommend, the approach that I think is, I talked about earlier, which is using this subspace approach with max volume trick to get a good basis. And you can see the errors in here, actually the red one, pretty nice. It's very pretty good. It doesn't evolve too much. This is this problem size. And by the way, these are the blocks I use for each of these different sizes. So 4 for this one, 8 for this one, etc., the 16 for this one, etc. And then this one is essentially the manifold approach using Newton, the subspace version of Newton approach, essentially the Chatelain version of it's a good implementation essentially of the Newton approach. This is, you can see it this could be viewed as a good implementation of this approach. And this one is the classical block-Jacobi, where you use full diagonalization, the standard one. All right, and you see, it's actually, the errors are very close to the original one, quite close, but no, slightly worse. And that has to do with the fact that you're doing the operation, probably more operations. It's really the only explanation I have. Okay, so that essentially finishes with this topic. I'm going to see if there are any questions regarding this before I move on to the next topic.
Yeah, so one question related to this greedy column selections. Does it related to the so-called stronger rank revealing QR method worked by Einstein?
Right. It's actually it's a whole class of different methods, and it actually you could also use something like that. Yeah, this is a form. This is a form of selecting just a good basis. It's not quite. You could view it as a form of that same thing as rank revealing QR. It's correct. Yeah.
So if I understand it correctly, the purpose is try to make that Y2 matrix to be well conditioned.
Yes, the purpose is to select. You have a matrix Q that's given here.
Yes.
Is to select columns. I mean, I put them together, but then I have to select columns here that are well conditioned. That's all.
Yeah.
So in the context of rank revealing QR, you have essentially something that looks like this, and you're trying to essentially do a form of permutation to get something that you have where you have something in here that's well behaved. It's a slightly different context, but it's in the same category.
So what's another maybe a quick question is asking, what does the Riccati added to the Newton-Raphson's iteration in a sense? Is it acceleration or?
What is it, Riccati, you mean?
Yeah, added to the, if we just apply the standard, the Newton-Raphson iterations.
So yes, the Riccati is required to solve for this problem here. So I'm not really sure. So once you have solved that, then you get your y that you use for the transformation. So it's not really, you don't solve it as a Riccati equation. You can solve it as a form of invariant subspace with using the approach I just talked about, the max volume approach.
Okay.
Did that answer your question? Yeah.
Yeah. Let's move on. Yeah.
Yeah. Okay. Yeah. So let's move on, and I'll talk with now this subspace iteration. So here I'm going to just quickly start with just a comparison of creative subspace methods and subspace iteration methods. So both of these methods are projection type methods. They use different subspaces, and they have advantages and disadvantages both. So creative subspace methods are fast. They tend to be optimal in a certain sense. And they require one starting vector. So this is some advantage. You can see it as a disadvantage in some situations too. Okay. And they're not easy to update. In part, that's one of the disadvantages of the requiring only one vector. If you have a subspace and you want to update that subspace, you're not really, it's not going to be easy if you need only one vector, all right? This is a disadvantage in some situations. And the changes on A are not easy to accommodate, right? So it's really, if A changes, then you really have to start from scratch in many situations, okay? So talking about eigenvalue problems here. The subspace iteration algorithm has this advantage that updates are very easy. If you're subspace, you have computed a previous subspace and A changes slightly, you just apply A to the subspace and you keep moving, no problem. This is really an algorithm that's geared towards subspaces as opposed to individual eigenvalues. And it's easy to accommodate changes in A. On the other hand, it tends to be a little slower. I'm not talking here about the context of only using MATVEX. If you use something like shift and invert, things are a little different. So let me discuss the one particular viewpoint where looking at subspace iteration is from the point of view of invariant subspaces is important. You look at, some of you know about the Constraint Equation, where you have an eigenvalue problem, and the potential here depends essentially on the eigenvectors, okay? Especially these two terms here, as you can see from the chart, the Hartree potential VH can be obtained by solving the Poisson equation, where rho here, the charge density, is this. It's a sum of the eigenvectors squared, in different locations R, and sum of the top top eigenvectors. So this is an eigenvalue problem where the potential depends on eigenvectors. So what you could do to solve this problem, what it's done is the self-consistent loop, where you solve an eigenvalue problem like this, where V is updated every time. So that you take the previous V, then compute these different terms that update the potential and come back and iterate. That's really a fixed point iteration kind of algorithm, okay? Very simple in concept. So now the question that you could ask is it important really to solve the eigenvalue problem accurately? Can we do something very simple? Can we just replace this operation here by a sort of filtering? And that's what this thing is about. So instead of solving the eigenvalue problem, what I would do is simply replace the step here by filtering. So each of these VI's, psi i's, will be filtered. It's in this form. I call it VI here. So I'm going to choose a polynomial that will enhance the eigenvalues of interest. And I apply that, and that's all I need. I don't want to compute the eigenvalues accurately. So essentially, there's the loop that subspace iteration loop of the eigenvalue problem that's merged with the outer loop. So I gain one loop from here. You can also view it as a nonlinear form of subspace iteration. Okay, or in a sense, what happened here is this operator has changed from step to step non-linearly, and you keep doing subspace iteration with it. That's the viewpoint that's updated here. So this is work we did ages ago, and the impact of this is you can gain a factor of 10 very easily from the standard approach because of the gain you get from essentially eliminating one loop. Okay, so that really comes from just looking at from the angle of subspaces and invariant subspaces. So now I'll move on to the a little further into looking at this invariant subspaces and looking at subspaces as objects. And I'm looking at now invariant Grassmannian perspective. So just a brief reminder, we call a Stiefel manifold, sometimes actually a compact Stiefel manifold in this case, the set of matrices that are n by p, where p is less than n, less or equal to n, such that y transpose y is an ID. So this is all set of orthogonal matrices. That's all there is to it. Okay, and the Grassmannian manifold is essentially what might call the quotient manifold. So essentially, I'm taking all of these matrices, a matrix Y, and then you can multiply it by a certain matrix, let's say Q here, which is P by P. Okay, if I did this, I get a different orthogonal matrix, but I get the same subspace. Generally, it's the same subspace. So you can view this Grassmannian manifold as the set that you get from the quotient set that you get from the equivalence relation that's set by this, right? Two subspaces are the same if they have, if they can be exchanged from one to the other by a simple orthogonal transformation. Okay, so that's all there is to it. You can view it. You can view this as a each point is the subspace of dimension P of Rn. And you can represent this G by using a certain basis V, okay? And in this case, we'll write it this way. But this is just a representative. So there's this paper, which is well known from the late 1990s by Edelman, Arias, and Smith, which defined a lot of tools for using Grassmann manifolds and for solving eigenvalue problems and optimizing essentially in Grassmann manifolds. And from there, you could see, you could get a couple of things that I will be using. One of them is the tangent space on the Grassmann manifold is a set of matrices are n by p, it's the same shape as y, such that y transpose delta is equal to 0. And this paper, essentially, as one of the applications, they looked at the eigenvalue problem that you get from minimizing or maximizing this trace over y, which is orthogonal, okay? So you do this by a Newton type approach, but now using a Grassmannian perspective to do that. So, and in this, the gradient of f of y, which I'll also be using, can be written in this form. So this is the gradient of this function at y. You could view it as y at the Grassmann point generated by y. So in that paper, they showed how to solve this problem. And these are just some of the details. You can solve this sort of Sylvester equation and actually expand it a little bit more. The pi is just this projection here, which I'll also be using. C is this, which I'll also be using. And in the end, you need to solve a Sylvester equation of this type. Okay, so these are some references. And I mentioned here this paper by Langan, but there are quite a few works related to this. I also should mention the paper by Asame and Wisniewski on the trace-mill algorithm. It's just in the same category. It's not seen that way, but it's exactly on the same form. So now let's look at specifically at the problem that I want to address. So the problem with the the technique I just talked about, which is the Newton type approach, is that you need to solve a Sylvester equation or multiple systems of equations. Now, there's no way of escaping that because it's a Newton approach. So can we do this without inversion? And the idea is to use a gradient approach or a graduate gradient approach. So this is just a reminder about the notation. This is the gradient of that function, what I called phi earlier. This is phi here. Okay, the gradient is this. Cy is this projected matrix. Okay, and I'm calling pi this projector. So the next point is to do a sort of a line search, right? I'm going to get y, and I'm going to go in the direction of g, adding mu g to it. So if I represent my manifold like this, I'm going to go in this direction, but this is not what I want. I want to project it back in here. So I'm going to do some sort of retraction, right? So this, in the paper by EAS, they do geodesic, it's just a little more complicated. So that's what I want to do. So I'm going to go in this direction and try to retract and don't try to maximize. For me, I want to maximize the trace. So this is going to be some of the details in here. If you look at y tilde here, what you find is that phi of y tilde is of this form, which tells me that, of course, this cannot go in, mu cannot be arbitrarily large because this would be, could go to infinity, but it's because y has to be renormalized, y tilde has to be renormalized. And because y transpose g is equal to 0, remember that this is the gradient, so this is satisfied, then I could see that y transpose tilde y tilde is equal to this matrix. Okay, and now this allows me to normalize it to the left, to the right. Okay, so now this is my, instead of using this matrix, I'll be using this matrix, and d mu is exactly this matrix in here. The 1/2 the square root of this matrix. This is diagonal matrix where you diagonalize G transpose G this way. So it may be a little bit, a lot of notations introduced at once, but the main point is that I'm taking this y here and I'm going to normalize it to the right by something in here, and that something turns out to be this matrix. U, which you get by diagonalizing this and then taking it d to the power -1, where d is this. So now this is not, again, a lot of notation here, but if you compute phi of y of mu, you get this expression here, which these are quantities you extract from here. So it's a rational function, which you can then minimize or maximize. In my case, I want to maximize. And because you know the derivatives, you know the shapes of these functions, each of these branches here. So it's very easy to come up with ways of maximizing this, all right? And therefore you get this algorithm that I'm describing here. This is a gradient approach where as long as G is still not small enough, I've diagonalized this matrix G, extract U and D beta, and then get this by some maximizing approximately this. And then I set the new Y, cut the new G, and repeat. That's my gradient approach. Very simple procedure. Any questions about this?
I think the purpose, just a quick comment maybe. It's more as a dedicated choice of a step size. People normally call that ingredients.
Right, yes, yeah, exactly. Yeah, this is a way of doing a line search here by essentially using what we know about the gradient of the, of the Grassmannian manifold and so on. So I could do this for any other method, but this thing is the G here is the gradient for this function phi that I defined earlier. So it's a line search, an exact line search. You can view it that way. Okay. So let's move on. Now, You could also use conjugate gradient, obviously. So here I'm going to use this Pollack-Riviere approach. All right. So in Pollack-Riviere, you have essentially an update of this type, where this G combines the new G and the old G, and you have this beta that's set up here, and you combine the old P with the G new in this form, the new gradient. I don't like to use iterates here like indices. This is a new gradient, and this is the new P, and the old one was without the index. So that's all. So you get the beta from here, you update this way. The only thing I had to add is to project back the gradient using this projector. So you do this and you project it back, and that's it. The rest is essentially straightforward kind of conjugate gradient approach with the framework I have set with this G. So that's exactly what I was talking about here. Okay, this work is still really ongoing. I want to just mention very quick couple of experiments. This is a simple example with the finite difference Laplacian. So it's a small matrix, and then I took another matrix from this with sparse collection, which is a small matrix of size. I think it's like 12,034. I mean 50. I think it's 5,400 or something like that. Okay. So in all cases, I'm taking dimension of dimension 8 for projection. So for there's also some details about the subspace iteration, and I wanted to make a couple of comments while I show the figures about the Chebyshev and so on. So, right, so I'm going to compare this method. I'm going to probably comment on them here. It's a lot easier. So let's look at what's shown on the left side here. On the left side, it shows only the progress of the trace as the iterations progress. So I'm using the gradient or whatever subspace iteration and looking at the trace of this 4x4 matrix or 8x8 matrix in this case. So I look at this for subspace iteration. Progress is not very fast, and I could use Chebyshev. This is the optimal Chebyshev, meaning using the optimal interval and what people do normally here. It turns out this is something I want to make as an observation again using the context of subspaces. That's not necessarily the optimal polynomial. You have to go a little bit inside the undesired spectrum to get better polynomial. And that's because you're not looking at individual eigenvalues, you're looking at a subspace. This is difficult to analyze. Where is the best polynomial? I think you can just go manually and find a good one. That's what I did in here. I just simply do, but that's all it just shows that you go inside a little bit, you do better. And these two that you see here are the conjugate gradient on top, and then the gradient, manifold gradient. And on the right side, what I'm showing is the error, norm of the error. This like invariance measure, right? So this norm here. And then you can see that the conjugate gradient does quite well, the black. And this is the optimal Chebyshev, which is this one here. And then the actual better Chebyshev, which is shown here. This is subspace iteration. The same thing with the other example. Actually, this is the size of the matrix I was looking for. And again, very similar curve, very similar behavior on the left side. Not as smooth for the conjugate gradient on the right side here. Okay, so let's move on to the next topic and see if there are any questions about these particular examples. No. All right, so no, okay, let's move on. So very quickly, the top.
Hello.
Yeah, yes, question. Yes.
Hi. Sorry, I kind of missed the first 5 minutes of your lecture, and I just wanted to ask. You mentioned all these methods, and I was just wondering what you were trying to solve. Like you mentioned the Newton-Ricartan iteration, the subspace approach with maximum volume, the subspace approach without maximum volume, manifold subspace
Right.
iteration.
Yeah.
And what are you trying to solve actually in this with these algorithms, please?
Yeah. So okay, this is the previous one. Actually, we'll go back to, I think
It's the first yeah. So
let's look at this one here. Yeah. So in this thing in here, these are different ways of getting that y that is used for the so there this one here.
Is this getting the y that is low conditioned, right?
Right, okay.
Ill-conditioned, an ill-conditioned y.
Yeah,
right.
Yeah. So
okay.
so that if you take this Q matrix in here, just selecting the best columns you can get to get a good y. That's right. So this one is shows only. So just taking the, actually I should have explained that. Yeah, this one here just takes the first ones and hoping for the best to get it's well conditioned. Okay, and this one, and then you can see that with max volume you could do, of course, infinitely better, and that's expected. This one is a standard approach, the classical using diagonalization, and this one is just solving the Riccati equation with the Sylvester equation, with solving this equation, the expensive way of doing it. Does that clarify it?
Yeah, that clarifies it. Thank you very much.
You're welcome. Sure.
Yeah.
So let's go back to this part in here and see again if there are any quick questions about this part. Otherwise, I will move on. Okay. So joint diagonalization. This is actually an interesting problem that I stumbled on by working with a colleague from University of Melbourne. The problem of joint diagonalization is a very important one in signal processing. What you do is the following. You have a set of matrices, P matrices that are symmetric, positive definite actually. These are covariance matrices. And you find a common matrix Q. These are all square now, okay? Such that Q transpose AIQ is close to diagonal, as close as possible to diagonal, all of them. Of course, you could do that with two matrices. That would be a generalized eigenvalue problem, right? But more than two is not possible to get an exact fit. You cannot get the exact diagonal. And so you want to get something where you minimize the sum of the square of the Frobenius norms of all the off-diagonal entries. That's what is used as a formulation. So that's the goal. Okay, so this deals with the case where AI is dense. And by the way, just as just kind of interesting coincidence here, the best known algorithm in this context is a Jacobi-like method. It's essentially a straightforward generalization of Jacobi to this case. And it's due to Cardoso and Soulamiac, and it's from 1996. The cost is order P and Q. So what do we do in the case where we have large matrices? It's not possible to use the same approach, obviously, but then you introduce these two measures here. So you seek, now we're going to seek a rectangular matrix instead of a square matrix. This is my Q. And I want to seek Q such that this Q is roughly invariant for all the AIs. And I want Q to be representing one end of the spectrum, for example, the largest one, okay? As much as possible. So this function here will take care of the first part, right? And then I would like my algorithm to take care of the second part, this point number 2. And that's what's done by this subspace iteration form of the algorithm. So this one just applies the subspace iteration, where for each of the matrices, you multiply the Q by A, and then you join all of the subspaces you get, and you reduce the, you do a Q, an SVD, you get essentially not an SVD, you get the dominant subspace from this, and you call that your new Q, and you repeat. Very simple generalization of subspace iteration. Well, you could also, this would be tested and works reasonably well. And we also looked at a Grassmannian perspective in this context. So you're now mixing this function, objective function, with the invariant subjective function. I want to get this large and this small. So I'm going to put a negative sign here at that. So it's a form of regularization. I want to mix these two to take care of mixing these two objectives. this is also has been implemented. And I probably don't want to spend too much time on this. I have very little time left for spectrum slicing. I just want to briefly mention what we want to do. I want to do a filtering approach. We're using Lang's method for this. So I'm going to get a filter of this type, and I insist on having something that's, if I have an interval that's in here, I insist on having something that's like this. It's, where everything above is accepted and everything below is rejected. So I'm going to go just to show you an experiment with this. So just go. I mean, maybe I'm going to go a little slower here. So the goal here is to extract the spectrum by pieces. So if I have a spectrum like this, I'm going to extract each of these pieces independently from one another, completely independently from one another. And the rationale is I avoid orthogonalization. I don't have to orthogonalize these vectors against these. It's not necessary. It will be given by the fact that they are orthogonal, okay? So here's a very simple illustration of what you can gain by doing that. This is from our code EVSL. You take 49 cubed Laplacian and use our code for using 1 or 2 or 3 or 6 slices, and you see the cost going down. This is even sequentially. And you can see the cost of the orthogonalization here in green, and the rest of the cost can be added. And here's the cost of MATVEX. It increases, but it's dominated, completely dominated by the rest of the cost. So that's why you see a decrease. And I want to just show one slide to finish up. I don't want to spend too much time on this. So here's I want to spend a few minutes on this, and then I'll leave it here. So here is the filter that I'm using. And I managed to have polynomial so that the desired spectrum is exactly what I want it to be, just this stuff in here. So everything above is desired, though this part here, oh, sorry about that. This part here is exactly this part, okay? And everything below it is rejected, is here. So what I will do is use Lang's with the full orthogonalization, and every time I extract an eigenvalue that's acceptable, it's in here, and I use the trace as a way of detecting when I'm done. So when the sum of these eigenvalues is good enough, I will stop. And that turns out to work because I'm looking at this perspective of eigenvalue of subspaces. And actually, this idea was gotten from looking at these applications in solid state physics, where the trace has a very significant role. And it turns out to be useful in this case. And this algorithm works. It will be hard to prove results like this theoretically, because you can get situations where it doesn't work. But in practice, this works. It's very high probability of getting the subspace you need. So I'm going to stop by saying a little bit of a commercial about this code. It's on our website. And this is my conclusion here. And I will say just that the block-Jacobi deserves really a second look. It's very useful to exploit algorithms for the using the Grassmannian perspective. Krylov subspace methods are not necessarily the best choices for all problems, but they could be extremely effective in other situations. They're very powerful for things like, the spectral density, which I didn't mention here. So I had finished about 1 minute or two before the end of the talk, so I'm going to leave it here for questions. Yep.
Thank you. Yeah. Thank you, Yousef. So enormous of rich and contents, and as always, very inspiring and encouraging. So excited to hear some of the old ideas and new ones.